Yes, students. Now we're going to discuss about speed control of three-phase induction motor. Okay, first of all, we know that the relationship between speed at different parameters is consists of induction motors. Okay, for induction motors, the speed equation is n is equal to ns into 1 minus s. This is the expressions, the speed of the induction motor. We can change either in the synchronous speed or changing the slip because the speed is depend upon the two parameters. One is a synchronous speed and another one is a slip. Okay, similarly the torque produced in case of three-phase induction motors is given by the torque is directly proportional to slip and voltage and secondary resistance. Okay, the torque is inversely proportional to uh, reactance and resistance. Okay, these reactants and reactants are changed, but the torque to maintain to be a constant for constant load condition. Motor reacts by changing its slip. Effectively, its speeds change. So mainly we are focusing for slip. Okay, what are the methods or uh, types are speed controls available in three-phase induction motors. In three-phase induction motor consists of two important parts. One is a stator, another one is a rotor. Okay, here in stator side, some methods of speed control available, as well as rotor side, some methods of speed control also available. Okay, in stator side, supply voltage controller, supply frequency control, some cases voltage and frequency ratio to be maintained constant, controlling the number of stator pulses in induction motor in stator, and adding rheostat in stator circuits. Okay, like that in rotor side, adding external resistors in the rotor circuits, cascade control, injecting slip frequency voltage in the rotor circuits. Out of these different types as, and now we're going to discuss about very few types as first method is supply frequency control. Okay, or V by F control. We know the synchronous speed Vns equal to 120 F by P. Controlling the supply frequency smoothly, the synchronous speed can be controlled over a wide range. This gives smooth speed control of an induction motor. But the expression for the air gap flux is given by 5G is equal to V by F. Here the voltage is directly proportional to air gap flux. At the same time, the frequency is inversely proportional to air gap flux. The remaining parameters are K1. K1 is nothing but it is a stator winding constant. Another one is a TPH1, that is a stator turns per phase. V is indicated as supply voltage and F is a supply frequency. Okay, this is the black diagram of V by F control. Here, this input AC supply, in this input AC supply, voltage and frequency are constant. Okay, first of all, we are using on converter. That converter is act as a rectifier. That rectifier is convert AC to DC. That pure DC is fed to inverter. Inverter is produced variable voltage and a variable frequency of AC voltages. That variable voltage and variable frequency of AC voltage supply is fed to induction motor. Okay, this one is a relationship between torque and plot of torque and torque versus slip. Okay, whenever the slip is zero, okay, the torque also zero. Okay, the slip value will be increasing, the torque value also increasing. So in these stages, the slip is directly proportional to torque. Whenever the torque is reached the maximum value, okay, at that time the value of slip is a maximum slip. After that, the slip value will be increasing, the torque value is going to be decreasing. In this region, the slip is inversely proportional to torque. Okay, in this graph itself we can clearly explain that before maximum slip, the slip is directly proportional to torque. Okay, after that maximum slip, the slip is inversely proportional to torque. In these conditions, the maximum value of slip is 1. Okay. So now we can clearly understand that in these equations, if your slip value is low, okay, the torque is uh, directly proportional to torque, sorry, slip. So in a low slip region, the operating region of induction motors, slip value is low, it's a negligible one. Okay. In this highly valued conditions, the voltage is directly proportional to the supply voltage. That means the rotor induced EMF is directly proportional to the supply voltage. Okay, this is the speed and torque relationship. Okay, in the nominal voltage, the maximum torque is high. Whenever the voltage value will be reduced, the maximum torque also reduce. This method is a very simplest method to change the stator voltage. Okay, the three-phase supply is not directly connected to the stator winding. Okay, through the auto transformer only, the input supply is connected to the stator winding. When we are changing the auto transformer, the turns will be changed, so the voltage will be changed. Okay, next one is here controlling the number of pulses. In this number of pulses, we are changing consecutive pulse method, multiple stator winding method, and another one is here pole amplitude modulation method. Here consecutive poles methods. Okay, it's consist of polarity state, south pole and north pole in magnet. Okay, in a consecutive poles methods, if your south pole is connected in one leg, another leg is a north pole, next leg is a south pole, next leg is a north pole. These rotations will be followed in supply. That means consecutive poles method. But uh, in this consequent poles methods consist of two types. One is this method, and another one is here two leg is connected in one magnet. Okay, through this diagram itself, we can clearly understand that two of the windings are connected in a same magnet, one same pole, that is a north pole. Another two pole is connected in the same magnet, that is a south pole. Okay, different types of poles is arranged. That is a pole changing method. Okay, next one is here multiple stator winding poles. NS equal to 120 F by P. Here P is indicated as a poles. Whenever we are increasing the poles, automatically the synchronous speed will be reduced because the poles is inversely proportional to the synchronous speed. Through this graph, we are indicated as a four pole machines having more synchronous speed is very high. Okay, in eight poles machine, starter poles, eight poles, it consists of eight poles means the speed is very low compared to the four pole three phase induction motor. And next one is here adding rheostat in a starter circuits. Okay, it's like yes, three phase starter resistance starter because this three phase supply is not connected directly to the stator winding through the rheostat. Okay, in each phase having separate rheostat. In starting stage, the rheostat is a maximum position, so that the voltage drop will be reducing. The voltage drop reduced, so automatically the current will be reduced. The voltage drop will be increasing. It's affected for the torque. The torque will be affected. The speed also controlled. This is adding a rheostat in stator circuits. Okay, if you are adding external resistance in stator circuits, the resistance is inversely proportional to torque. Okay, we know the torque equations of three phase induction motor. Okay, in a denominator it's a r2 squared. Okay, in low slip regions, the r2 is a negligible one, but um, high slip regions, the resistance, rotor resistance is considered. The rotor resistance value will be maximum. The torque is decrease. When the load of the motor is same, the motor has supplied the same torque as load demand. So motor reacts by different types of torque value. Okay, so the torque will be changed. The motor speed also changed. Okay, in this graph, in the maximum torque level also indicated the normal resistance value is somewhat less than maximum torque, but whenever the torque the resistors will be decreasing, the starting torque also increasing. Okay, these are the different types of speed control methods is available in three-phase induction motor.